just to get this, okay? Because this is real straightforward. And we're recording. Put this system into the format, matrix format. Actually, well, it's easy to write down the matrix. 2x minus 3y equals 7. There it is, and so forth. So we understand that we can invert this matrix, multiply on the left by the matrix. Step you should probably consider writing down, just continue reminding yourself of the algebra. And we get this, okay? So we'll great, right? We get down to here, we reverse these because this is a 2 by 2. We don't have to do the augmented matrix with the identity and reduce and so forth. So we switch the main diagonal, change the sign of the secondary diagonal, and of course we have to divide by the reciprocal of the determinant. The determinant is 0. So the inverse doesn't exist. Why does the inverse not exist? Well, among other things, if you write out the equation or the matrix here and reduce it, it's going to reduce to this with row zeros, meaning that you have a system that has no solution, or possibly a system that has infinitely many solutions. It means that this line is parallel to this line. Okay? So there are a bunch of equivalent conditions to matrix reducing to something with a row of zeros. Okay? Here's 1. Here's 2. Determinant is 0. 3. Either no solution or equally many solutions. 4. If it's a 2 by 2, the lines are parallel, meaning either they're the same line or they're completely different, meaning either you have infinitely many solutions, you have one free variable, okay? And if it says there's no solution, well, you can go back and think about the free variables. I don't want to take the time to write all that out because we took a little longer in the quiz. Okay, so 2 by 2 lines are parallel. Yeah, there are other conditions. You understand these. If it's a 3 by 3, your planes are parallel. You can understand all that, the geometry of it and everything, especially in the 2 by 2 case, where you can just draw lines, okay? Move straight lines. If you were to graph it, you find that there's no solution. If you graph it accurately. Okay. So that's the lesson of the first equation. Now the second one is solved in the same way, but it probably will have it will have a solution, because these coefficients are both positive. One of these is positive, one is negative, okay? So whatever your numbers are, this one would work out. You wouldn't get a determinant of 0. You would have an inverse, and you just multiply it by the 5/9. Okay, now, that's kind of review, but you really have to understand that to understand what's coming up about vector spaces and so forth. And I gotta find out why these things keep popping up on my system. Okay. Now, so for the third problem, we want to set this up in the form of a matrix, okay? I advocate that you write out the system of equations, okay? So we got C1, V1 plus C2, V3 plus C3, C2, V2 plus C3, V3 equals W, okay? Well, you could plug in the numbers. I'm just going to say that equals W, okay? For W to be anything, it's going to differ depending on your numbers, okay? Well, what's this tell us? This tells us that C1, 3C1, 2C1 plus 2C2, negative C2, C2, plus 3C3, 2C3, C3 equals, we'll call it W1, W2, W3, which tells us that C1 plus 2C2 plus 3C3, 3C1 minus C2 plus 2C3, 2C1 plus C2 plus C3 equals W1, W2, W3. So C1 plus 2C2 plus 3C3 equals W1, 3C1 minus C2 plus 2C3 equals W2. And I'll copy these down, right? 2C1 plus C2 plus C3. That should be a 2C2. 2C3. 2C3. Yeah, well, it should be a 2C3, okay? Equals W3. Okay. And now, this tells you that the matrix is multiplied by C1, C2, C3. That's equal W1, W2, W3. So what's the matrix? 1, 2, 3. 3, negative 1, 2. 2, 1, 2. Okay. And it should be 3, 1, 2. I'm sorry, this mask, I really can blame this on the mask. So, we need to have a mask. Now this should be, well, okay, here's your first vector, your 1, 3, 2. Maybe this is right. Okay, 2, negative 1, 1, and 3, 2, 2, but it should be 3, 2, 1. So this should have been a 1, C3 up here. So I thought I'd made a mistake to add it. So that's a 1. And I think I've got it correct. And if not, you know what to do. Okay. Point is then, that would become a 1. And we would see the vectors V1, V2, V3. Times your C1, C2, C3 equals W1, W2, W3. It doesn't really matter what W1, W2, and W3 are, because it didn't ask you to solve it. I asked you to set it up. Okay. Now, if you just write down the vectors, you might accidentally write the vectors as rows. You might not remember whether to write them as rows or columns. If you don't think back, or in current case, I think you really should slop this down somewhere off to the side and make sure you got them right to keep reminding yourself of how these things have to work. And then think about why they work the way they do. So I could explain it the way I look at it, but you just have to figure out how you look at it. Okay? And the way I look at it, I haven't done this for a while. I write the stupid things down. I know this, but I want to remind myself of why this is the case. Okay, and of course, this constitutes, remember that commas separate columns. Okay, when you write vectors out, when you write matrices out, you know, that's a convention that you use when you write a matrix into WebAssign, right? And semicolon, I think that's it. But anyhow, and actually, well, I'm going to write it like this. This would actually be semicolons because they separate columns. But anyhow, V1 is in a column, V2 is a column, V3 is a column. And there's your matrix. And that's a matrix you would invert to solve this equation. And if the determinant of this matrix is 0, what's it tell you? Well, it tells you that this matrix would reduce the one with the row of zeros. What's that mean? That means 5, at least 1, one row is the sum of multiples of the other. And what's another word for sum of multiples? A linear combination. So I'll write that down. Might be a little hard to read even on the video. Resolution's pretty good. It's probably legible. At least one row is a sum of multiples of the other, and sum of multiples is a linear combination. Okay? And that's really the probably most important concept in this chapter, or at least the most fundamental concept that the other concepts are built on. Which is why I wanted to do this quiz before we move on into the idea of vector spaces, subspaces, bases, etc. Change of bases. It gets pretty challenging by the end of the chapter. Okay. And then it leads into some really neat stuff. So it's worth the agony. Well, so I want to tell you what a vector space is now. First place, vectors in R2 and R3. The scalar multiplication by real numbers, okay? And I'm not going to be real specific about that. But right now, we're talking about you multiply a vector by real numbers. We did in this example. Scalar multiplication and vector addition. Is a paradigm vector space. Okay. Any other space that shares these properties is a vector space. Okay, so vectors don't have to be arrows in R2 and R3. For example, 2 by 2 matrices could be your vectors. You can multiply a 2 by 2 matrix by a scalar, right? Okay, just multiply all of them. After by the scalar. You can add 2 by 2 matrices. Okay. 4 by 3 matrices. You can add those. You can multiply by scalars, right? They add just as well as ordered triples or ordered pairs. Okay. And we're going to see some details of that. The key properties just properties of your vectors in R3 or R2 or Rn or whatever. Okay. Okay, CV1 plus CV2 equals CV1. Okay. That's a distributive property. Okay. And here's a big one. Okay, I'm going to say key properties for the vector space V. That's a capital V, and just to distinguish it from vectors, I'll make it a really fancy capital V, okay? Not all that fancy. I could do curly Q's to make it fancy, that'd be fancy. Okay, well, if V1 and V2 are in your vector space, then CV1, CV2, and V1 plus V2 or NV, okay? That's a big one. This is called closure. It wouldn't make sense to have a vector space, and then two of the things you think are in the vector space, you add them, and they aren't in the vector space anymore. Or you multiply it by 12, and it's not in the vector space anymore, right? You want to keep them in the vector space, and if it doesn't work, then you don't have a vector space. Okay, that's going to be real important when we talk about subspaces, which I hope we can talk about today. Okay, so V1 and V2 are in the vector space, then any multiples or sums of those vectors, or sums of multiples, because by extension, if CV1 and CV2 are in the vector space, then CV1 plus CV2 has to be in the vector space, because CV1 and CV2 could be your vectors V1 and V2. Okay. Now, these are in the vector space, so this has to apply to them, so that CV1 plus CV2 has to be in the space. You want to think about that a little. Okay, because these are not real familiar properties. These should be familiar as properties of the real numbers. But as I say, that probably hasn't been stressed as much as it ought to be, because it's a little bit abstract, and when we're trying to teach algebra 2 to everybody and his brother, people that could understand the properties get left out because most people can't understand them. And so you got to do a little catching up and I just want you to be aware of that. Okay, that could be you had a masterful teacher in Algebra 2 and some of your other courses, and really were able to address some of these abstract properties. But kind of rare that happens. Okay, and kind of rare that you have homework that actually asks you to do that. We're going to have it now, so you got to get used to it. Okay, so anyhow, so other properties. Let me get my notation. But the idea is simply that you got a zero vector. If you add zero vector to any other vector, it doesn't change that vector, right? V plus 0 equals V, just like a number plus 0 equals that number, right? X plus 0 equals X. So this allows us to do just regular algebra. A lot of regular algebra in vector spaces. Okay. This is of identity. Okay. If V is a member, the vector in your vector space, and introduce you a little annotation with backward capital E means there exists a vector negative V in your vector space, such that V plus negative V equals 0. This means such that V plus negative V equals 0. Okay. These are easy notations to understand. You know, I saw them in high school, and everybody else saw them, and everybody understood them. Okay. Of course, you know, we had more selective classes back then. It was actually the senior level math class where we saw this. So if you haven't seen it, it's worth understanding. So, you know, if you go back to this point in the video, this says there exists V, a member of the space V, such that you add V to negative V, you get the 0 vector. And that's additive inverse. The additive inverse property. You could say, you know, 0 times V is the 0 vector. Okay. Now, if you multiply a vector by the 0 scalar, you get the 0 vector. Okay. Now we've got to be careful. That's the 0 vector. This is the 0 scalar. You want to think about that a little bit. Okay. Well, those are some properties. There might be others we want to talk about in the book list. And depending on how they're listed, you could have 10 properties, 8 properties, 12 properties. Okay. I don't even remember how many your book has, but there's a sufficient set of properties. I kind of think some of them follow from others. So I think you could actually take that list a little shorter, but maybe I'm not thinking that, so we'll see. Okay. And we might not see, but you know, the properties your book gives us, the properties, you should know what the properties are. You should be able to test. Okay. And you should remember that these, at least these, are the main properties, the ones that you end up having to test a lot the remaining properties. If you really want to test something to see it's a vector space, you test all the properties, just to be sure. But the ones, if it has these properties, usually it's going to have the others. Okay, so let's consider a vector space. Okay. Here we just say the set of real 2x2 matrices, meaning all the entries are real numbers. Okay. You could also have matrices with complex numbers and complex scalars. Okay. And that becomes important in the last week of the course, where we really see what this stuff is headed toward by doing complex vector spaces. If you understand the vector spaces that we have before we get to complex vector spaces, you'll see something really kind of neat. Okay. If you don't understand it, you're going to have to fake it. Okay. But don't get in a position where you're going to want to fake it, especially when you make an A in the course. Right? And you should make an A in the course. Everybody should. I hope everybody will. Not going to make it easy on you, but you'll try to be reasonable at least. Okay. It's a tough thing to achieve, but well worth it. Okay. So we want to test to see if this set of vectors and this set of scalars satisfies these equations, right? So first of all, test closure. That's often the first question we want to ask about a vector space. Is it closed? Well, I'll write this out a little more formally. Let these two vectors be members of your vector space V. First of all, does this accurately represent members of your vector space V? Well, yes, because V is a set of 2x2 matrices. Okay. These are 2x2 matrices. Then, and let's call this A. Just so I can write things out. Okay. So you would understand what I meant. Okay, then A plus B. Or actually, let's not call them A and B. Let's call this V1. Let's call this V2. Okay. Then V1 plus V2. Well, if we have time, I'd ask you to write this out. Okay. But it's pretty clear. You're going to have A11 plus B11, A1. Okay, right? Okay. And V1, V2 are real matrices. Now, if you want to write this out in detail, you'd say, these are real matrices, so these are all real numbers. So you'd say A11, or the AIJs are real, and the BIJs are real, right? You want to do a formal proof. Then you would say Sum of two real numbers is a real number. So the aij's plus bij's are real, right? So now we're actually going to write that out. Okay. These are real, so B1 plus B2 is a real matrix. Real, and it's 2 by 2. So that B1 plus B2 is a member of the vector space V. So it's closed under matrix addition. Okay. As it's closed under scalar multiplication. Well, since your scalars are real numbers, then if you multiply a scalar times this matrix, you're going to get scalar times this, scalar times this, scalar times this, scalar times this. Your scalars are real numbers. These are real numbers. So you now have a real 2 by 2 matrix. Example, and you kind of want to make note of this. I'll just say yes in parentheses, meaning you have to think through how to verify that, but just what I said. In your book will have examples. If these are sort of real matrices, and you have scalars that are complex, this is not closed. Under scalar multiplication. Because if you multiply this matrix by 2i plus a square root, or 2 plus a square root of 3i, something you'd easily get from a quadratic equation, right? Then all of these would have imaginary components and they wouldn't be real anymore. Okay? So make sure you understand this. Now, if these are all complex and your scalars are all complex, it's fine. Okay? If these are all complex and your scalars are all real numbers, then you would have closure under scalar multiplication, because a real number times a complex number is a complex number. Your matrix would be complex. You multiply it by 7, it's still complex. Okay? Now, other things would get in your way there, or you might think about what would happen. But you know, that's a couple of months in the future where we've really got to think about it. But you know, just as an example of a field of scalars, okay? Think real numbers or complex numbers. You could also have rational numbers, irrational numbers, which would lead to violation of some of the properties. because you multiply two irrational numbers and get a rational number. So, or add two, whatever. Square root of 3 and 1 minus the square root of 3 are irrational numbers. If you add them, you get 1, which is a rational number, an integer in fact. Okay. So your field of scalars could be a lot of different things. In this course, the only fields we're going to be looking at, for the most part, are real numbers and complex numbers come later. But I wanted to warn you about that. So there's a property of closure. Okay. What's some of the other properties? Okay, we got everything here, yeah. How far can you go over here? Yeah, you get all the way over. Good. Okay. Most of these are really easy and obvious. Closure is the one that will most often trip you up. That's really the first one again that we look at. Okay, well, let's look at another example. Okay, I'm just going to look at closure. Because again, the others, you just kind of write them out and look at them, look at the examples. I don't think you'll have too much trouble with them. So another one that seems a little weird is polynomials. And this extends into a really important set of applications. Your vectors can be functions. Okay. For example, a set of all continuous functions. If you add two continuous functions, it's continuous. Okay. Continuous, what's continuous mean? Okay, well, you just had first semester calculus in most cases. Continuous means the limit of f of x as x approaches a equals f of a for all values of a. Okay. And if it's true for f and if it's true for the function g, then it's easy to prove that it's true for both functions because of limit properties. Now, I'm not going to go into the details of that, but it's kind of thing that is kind of important to know. Okay. And your book's going to give you examples. And I'm probably not going to go over them today because I want to actually talk about subspaces a little bit. Okay. And we've only got like 10 minutes. Maybe I won't get to talk about subspaces, but we'll see. Okay. The scalars be real numbers and vectors and polynomials with real coefficients. Of degree less than or equal to m. And in this case, let's say a degree less than or equal to 2 because it's easy, okay? So the typical polynomial would be ax squared plus bx plus c. Is this closed? Well, without getting real formal about it. Consider that if you got two polynomials with coefficients A1, B1, C1, and A2, C2, A2, B2, C2, okay, that this equal this, right? Well, is that a polynomial of degree less or equal to 2? Yeah. Degree is 2, right? Highest power of x is the square. And if A1, if all your coefficients are real, then when you add two coefficients, they're all going to be real. So this is all real coefficients, right? So this is a polynomial of degree less or equal to 2. Is there an identity? Okay. Now we didn't test identities. You could write it as 0x squared plus 0x plus 0. Yeah, that's the additive identity. You don't have a multiplicative identity, okay? And you don't have division. You can't divide one vector, if vectors are arrows in R2 and R3, you can't divide them. And you can't multiply them in any way that satisfies the axioms, okay? There are vector products, interior and exterior products, and all kinds of stuff, but they don't obey the rules of that we're used to in algebra of real numbers, basically. Okay? And of course, you got to do some examples to see that. So we have this, okay? Inverse. So ax squared plus bx plus c is negative ax squared minus bx minus c. Very simple. Because first place, if you add this to your typical ax squared plus bx plus c, you get just ax squared plus bx plus c. And that's pretty obvious, right? And it should be obvious then if you add this and this, you get this, okay? So the properties are pretty obvious, but you got to think through them because it's a little weird going from arrows to polynomials. Of course, this means that you could express all these polynomials as arrows, okay? You could identify them with arrows, this arrow being the A, B, C vector, okay? And you could even do matrix operations on them. Transform them, whatever that means, we'll see soon. Okay. So that's another example. And there are a couple of properties that are obvious and easy to prove, but you gotta prove these properties for a number of different vector spaces. Okay. So that you really understand them, understand how they work. I'll just say it because I do want to talk just briefly about subspaces. So we start those neurons firing. So we can talk about it more deeply next week, along with some other stuff that you're going to need. I said continuous functions, okay? If you add two continuous functions, you get a continuous function. If you multiply a continuous function by the zero function, about that by zero, you get the zero function, which is nice and continuous. Okay, it's perhaps a nice flat line along the x-axis, right? Okay, differentiable functions. You have two differentiable functions. Take the derivative of this one, you take the derivative of this one. then you can take the derivative of the sum, because the derivative of f plus g is the derivative of f plus the derivative of g, right? Okay, those properties. And you're going to see a lot of those properties when you read the section and look at the examples. Okay. So that ought to give you some feeling for the idea of what a vector space is, and vector spaces can be a lot of things. Okay, make sense? Okay, now subspaces. And I'm going to try to give you an example of a subspace, a subset that's not a subspace. It's a subspace W of V. It is itself a vector space. Now it turns out you don't have to prove every axiom to prove that something is a subspace, because if it's in the vector space, it's going to inherit a lot of the properties of the vector space. Okay? Doesn't mean it inherits something like closure. So let's check closure. Okay. Let V be the space of 2 by 2 matrices. Let W be the set of symmetric 2 by 2 matrices. Okay. Well, if you add 2 symmetric matrices, the sum is symmetric. Remember what symmetric means? It means everything above the main diagonal is reflected below the main diagonal, right? So it's symmetric here. Those are the difference. Okay. Now, does a set of 2 by 2 matrices have an identity? Well, the identity matrix is symmetric. It's got zeros on both sides of the diagonal. It's symmetric, okay? Inverses. Yeah, the inverse of a symmetric matrix will just have the yeah, there's a little complexity to that. I'd have to write it out, so I'm not going to say. You can think about it. Okay, just take the matrix 3, 4 here, and 7, 7 here. Okay, what would the inverse be? Okay, and it turned out that you'd have to have the inverse adds up to 0. Okay. Well, actually, just have to have the negative involved. Okay, so I was thinking about something else. It's easy to show that. Okay. U equals matrices. Not a subspace. You can add two singular matrices and get a non-singular matrix. Okay. Set of two singular matrix doesn't have to be singular. Okay. You had a singular matrix in your quiz. The first matrix was singular. It reduced down to row of zeros. It didn't have an inverse, etc. Right? Okay. You can have two such matrices that add up to something non-singular. Okay. Then some two matrices that have zero determinant doesn't have to have zero determinant. Check that out. And it's easy to see. Just basically make up any two matrices. Okay. And see what happens. And see if what I said is even true. Test it yourself. Okay. Okay. Well, we're out of time. Your assignment for next time is just question 4.2, which is on subspaces. But it's important to really understand them so it's easy to understand. Did I say subspaces? Vector spaces. Okay, you want to understand vector spaces real well, and then it's fairly easy to understand subspaces. And you have to answer questions like this. Okay, and then there's another section yet we need to prepare you for. It'll be due next Tuesday, okay? Or maybe Sunday. We'll see. I forget how the assignments are arranged. I will comment